I'm Tsubasa Michifuji from the University of Tokyo, a member of Miyata-san's laboratory, and today I will talk about this title, Photometric Accuracy with Multi-Field Imager and Mid-Infrared Wavelengths. So first is introduction. In Miyata-san's talk, Phil Tucker will overcome difficulties in mid-infrared monitoring observation from time fluctuation of atmospheric transmittance. This is the image of Phil Tucker, and we can get two images like this and distant target, and its maximum separation is up to 25 arc minutes in Tau Observatory. Okay. So with using this system, field Tucker, we aim at photometric accuracy with a few percent using the two field of views. Okay. So we use the two field of views. We must make precise photo threading. Practically, we aim at its error is less than 1% or so. this value is much less than a few percent. Okay, but the photo threading is very difficult problem in mid-infrared wavelengths now. Then after that, we evaluate the effect of canceling influence of atmospheric transmittance changes by field Tucker. Okay. To verify these points of field Tucker, we did the engineering observation of field Tucker and data analysis. The engineering observation is held on 2018, and the date targets separation wavelengths is shown here. And the separation is 4.3 arc minutes, and wavelength is N band. And after that, at last, in data analysis, we evaluate the change of counter ratio of those two targets. Okay. So the next is the flow. This is the flow chart of data analysis. This is the raw data, and we did the chopping observation technology. So we did the chopping subtraction, like chop A minus chop B or B minus A, like that. And can you see these stars here, here, and here, or here? And this is the borderline of field Tucker. Okay. So the next is we make the flat threading from chop B for chop A images. This is because the flat threading, if we use the chop A images for chop A flat threading, the star position is the same, so this is not good. So we must make the flat threading for chop A from chop B. Okay. So after the flat threading correction, this is the final results of this data, and P1 and P2 shows the 1 and 2 shows the different field of views, so different stars. Okay, but P shows the same chop of observation, so P1 and P2 is the different stars, but they're taken at the same time. Then also the P1 and N1 is the same star, but taken at the different time. Okay. At last, we did the virtual photometry. The next slide is how to make the flat threading, and focus on one pixel, the incoming photons, and pixel count shows the not relationship, but like this curve. And in the mid-infrared, incoming photons changes by atmospheric transmittance environment. So it has some range like this, okay. In conventional method, like Subaru comics, the upper half one, we take 0 point and one representative point in the observation range and fit them linearly, and we regard its gradient as the flat threading value. But in new method, the lower half one, using the range of incoming photons, we take many points like this and fit all of them linearly and regard its gradient as flat threading value. And also we can evaluate the flat threading value as the fitting gradient error. Okay. However, we can't know incoming photons strictly, but we only wanna remove the flat fading difference between pixels, so we don't need to correct in absolute value of this gradient. So as the horizontal axis, we use the background average counts, and in this way, we can correct the relative flat fading difference between pixels. And this is the result of this fitting of at 1 pixel. The horizontal axis shows the background average count, and vertical axis shows the pixel count. We can see the very tight linear relationship, and its gradient error was 0.275%. Okay. So, and this is the all field of views flat error image, okay, flat error, and its histogram. They show the mostly 0.2%, this orange color, and 0.2 to 0.3%, okay, and which means the very much less than a few percent. So we could make the enough precise flat fading. So finally, we did the aperture photometry, and this is the final image of Posey and neck. And this is the results of aperture photometry, and the P1, P2, N1, and so right curves shows the same time fluctuation. The horizontal axis shows the time in minute, the up to 60 minutes, this field, and the vertical axis shows the still total counts. Okay, so we can see the almost the same time fluctuation and of these stars. Okay, so finally we calculate the count ratio of different stars at taken at the same time, which means the ratio of P1 over P2 or N1 over N2. Okay. So this is the count ratio versus time, and we can see we could remove this time fluctuation and very constant value. Okay. So
yeah,
okay.
sorry.
We calculate the average of count ratio and standard deviation at each count ratio, and this value we get this value, and finally we get the standard deviation over average as the value of this ratio, and we get the 1.83% and 1.86% as the error of count ratio. So we could achieve the aperture photometric accuracy with a few percent. So in conclusion, we could make the enough precise flat fading. Its error is about 0.3% using the time variation of atmosphere. Okay, and also we could do the about 2% photometric accuracy using the field stacker. But in this work, this data shows the 60 minutes time scale in band and 4.3 arc minutes separation. So the tau max scale is the 25 arc minutes. So in future work, we must do the longer time scale, other wavelengths, and larger separation. Okay, that's all. Thank you very much.
Okay, thank you. So I think I will look at the Slack. Okay, so there was a first question by Leo about opportunities to do science opportunities for doing accurate photometry, but it was mostly discussed. But of course, please take a look at the Slack channel. And yeah, the question from Mario. Do you have any plans to establish a more accurate system of absolute mid-infrared standard stars with your accurate differential photometry?
Actually, no, we don't have any plan to establish absolute calibration, but we understand its importance.